Welcome to Discovering the Unknown, where we explore the strangest frontiers of reality, from worlds hidden beneath ice to mysteries buried under miles of water. Here, science meets the unknown, and every discovery forces us to rethink what life is and where it can exist. The ocean NASA is racing to understand. What if I told you NASA's next moonshot isn't just upward, it's downward? Far below the waves, in total darkness, under pressure so intense it would compress your bones, lies a world that looks like science fiction and behaves like another planet. It's a place of hydrothermal furnaces, towering chemical plumes, and ecosystems that run on rock instead of sunlight. And for the space agency, the deep ocean is not a curiosity. It's a laboratory, a testing ground, and a blueprint for finding life beyond Earth. Tonight, we'll follow NASA's hidden mission beneath the waves, why the agency sends engineers and robots to the abyss, what they're searching for, and how discoveries at the bottom of our oceans could reshape everything we believe about life in the universe. Why NASA goes underwater, analogs, instruments, and astrobiology. You've seen astronauts train in giant pools, but those exercises are more than PR. The ocean gives NASA a real-world arena that mimics the isolation, hostile conditions, and operational constraints of extraterrestrial missions. Programs like NEEMO, NASA Extreme Environment Mission Operations place astronauts and researchers inside the Aquarius undersea habitat to practice long-duration living, extravehicular tasks, and teamwork in a cramped, demanding environment. A rehearsal for missions to the Moon, Mars, or icy moons with subsurface oceans. The lessons are practical: life support reliability, human factors under stress, and designing tools that work when every movement and supply line is expensive. Looking for life where life shouldn't exist. But NASA's interest goes deeper than training. The agency is hunting biosignatures, the chemical and textural traces of life, in places on Earth that mirror alien environments. Hydrothermal vents on the seafloor, where scalding, mineral-rich water pours from cracks in the crust, are powered not by sunlight, but by chemistry. Microbes at these vents harvest energy from rock, chemosynthesis, the same process scientists believe could power life in subsurface oceans, on moons like Europa and Enceladus. Studying vent systems here lets NASA refine life detection strategies for missions that will probe faraway oceans under ice. Technology transfer. Robots built for Mars, tested in the deep. To look where humans cannot go, NASA and its partners build autonomous robots, machines that can endure crushing pressures, corrosive saltwater, and complete darkness. Jet Propulsion Laboratory engineers are adapting navigation, autonomy, and perception systems originally developed for Mars and applying them to the ocean. Projects like Orpheus, an autonomous underwater vehicle developed in collaboration between JPL and Woods Hole. Borrow terrain relative navigation and vision-based autonomy techniques used on planetary rovers, enabling long-duration, untethered exploration of the Hadal deepest zones. These systems let robots make real-time decisions when communications delays or loss make remote control impossible. The lesson of failure: why deep ocean work is hard. The ocean's hostility is not hypothetical. Hybrid vehicles like Nereus, built to reach the deepest trenches, succeeded spectacularly, then failed catastrophically under extreme pressure, imploding during a 2014 dive. These losses are grim but instructive. They expose engineering limits, drive materials research, and force better mission design. NASA and oceanographers treat those failures as prototypes, hard-earned lessons. The same way early Mars landers taught planetary engineers to build better entry systems. Each implosion or lost probe narrows the path to a reliable deep ocean explorer. What NASA is actually looking for at the bottom. So what does NASA hope to find on the seafloor that might change everything? The searches fall into three overlapping categories. 1. Natural laboratories for life, environments such as hydrothermal vents, cold seeps, and subsurface rock-hosted aquifers, where chemistry could support microbial communities independent of sunlight. These communities are analogs for potential life in subsurface oceans on icy moons. Studying their metabolisms, community structures, and chemical fingerprints helps NASA design instruments that can detect similar biosignatures elsewhere. 2. Instrument validation, testing sensors that measure trace organics, isotopic ratios, and microscopic structures in situ under real-world pressure and temperature. A successful life detection sensor must work when it's dark, cold, and under thousands of meters of water. The deep ocean is the perfect stress test. 3. New physics and chemistry. Discoveries at vents and in trenches continually rewrite our chemistry textbooks. Unexpected mineral assemblages, abiotic sources of hydrogen, or exotic organic synthesis pathways that could widen the range of habitable chemistry we consider when searching for life beyond Earth. Every novel geochemical process found here broadens the kinds of places we'll look for life in the solar system. Hydrothermal vents, life without sunlight. One of the most profound discoveries in modern science came not from space, but from the ocean floor. In the late 20th century, scientists discovered hydrothermal vents, towering chimneys spewing superheated mineral-rich water into the abyss. Around them thrived dense ecosystems of worms, clams, shrimp, and bacteria, life powered entirely by chemistry, not sunlight. This shattered a long-held assumption: life does not require the sun. Instead, microbes at vents use chemosynthesis, extracting energy from compounds like hydrogen sulfide and methane. These ecosystems exist in complete darkness, extreme pressure, toxic chemical conditions, constant geological instability. To NASA, this discovery was seismic, because if life can exist here, then life could exist beneath the icy crust of Europa. If you want to explore the hidden connections between Earth and the cosmos, the places where science meets the unknown, and the discoveries that could rewrite humanity's place in the universe, subscribe to Discovering the Unknown.